right, I'm gonna get started talking about a couple things. So real quick, before we start this section today, I want to talk a bit about piecewise functions, because piecewise functions were not people's most favorite parts on the quiz. So a piecewise function is a function. Okay, so if I give you an input, you should only give me one output. It looks like there's going to be two outputs, but there's not. You just have to figure out which output you actually get for piecewise functions. Okay, so for example, right, if I ask you what f of 5 is, we only use one of the pieces. And to determine which piece we use, we have to look at what x is. Right, x is 5. So which piece do we use? We use the bottom piece, because the bottom piece is the one you use when x is positive. So use bottom piece. That's what we're doing with these piecewise functions. So f of 5 is only 5. But for example, right, if we have something like f of negative 2, well, now x is negative 2. If x is negative 2, we have to use this piece. This is the piece, this top piece is the one we use when x is negative. So it's going to be negative 2 squared plus 5, which is 9. Right? So the whole idea for piecewise functions is you just have to look at what your input is. Your input tells you which piece of the function to use. All right. This is kind of what I wanted to talk about for stuff I saw on the quiz. Just a little bit of review on piecewise. All right, and what this graph looks like is it's going to look something like this. For negative numbers, it looks like a parabola that's been shifted up. For all the other numbers, it just looks like the line y equals x. So this is the actual graph of this function. No, you don't find both, Lane, because there's only one answer. Anytime you use a piecewise function, there's only one answer, right? When f is 5, right? If this is 5 and this is 5, right? When x is 5, there's only one y value here. There's only one function value when x is 5. So the answer, f of 5, is just 5, because you're on this part of the piece. And at negative 2, it's only 9, because when x is negative 2, there's only one function value right here. So what you do to evaluate it, if you don't have the graph, if you have the graph, I'm confident you could all evaluate it, but you're probably not going to have the graph. You just need to figure out what your x value is and then see which piece you use. So here x is 5, so 5 is greater than 0. We use the bottom piece for everything that's greater than 0, and that's why we just said, okay, f of x is just x here. There will always be only one answer because it's a function. And the definition of a function, right, is that every input gives only one output. Yeah, so that's a good way. That's a good question, Bella. Good. So again, we could do some more of these. When x is 0, which piece do we use? The top piece. So it's going to be 0 squared plus 5, which says just 5. That's the only answer. F of 0 is only 5. Again, when f is, I don't know, negative 1, x is negative 1, so we use this top piece, because we use the top piece for everything that's less than or equal to 0. So we're going to have negative 1 squared plus 5. All right. Any other questions about piecewise functions before we actually get into the material for today? And as a reminder, right, we're doing 3.5 today, but it will not be on the exam that's tomorrow. Exam tomorrow only covers up to 3.4. Tomorrow there will be no lecture. There will just be the exam at class time. from 1 to 2:30. I'm giving extra time if you need it, all right? So tomorrow will just be the exam, no class. Friday's a holiday. It's Easter holiday, so we will not be having class. I cannot speak for your other classes, but we will not be having any class. So after today, shed a tear. After today, we will not have another math class until Monday. So I hope you can survive. Now, today's going to be normal class. I originally was planning on having review days for 1400, but because we just lost a week, I don't think we can really have review days unless I go through the material like lightning fast. And I think if I go through the material lightning fast, I think that's going to be bad. So I'll continue answering questions via the Discord. If some questions that you ask in Discord have quick answers and I can just type back to you. But if we need more of a dialogue, we can, Discord also supports video and phone calls. All right. So, just as necessary, feel free to ask me. And again, I will not be available 24 hours a day, but you can still send a message 24 hours a day. And if I'm available, I will respond. And if I'm not available, I will respond when I am available. Okay. So it's always better to just send a question that you have and I can get to it. Maybe I'll be on my computer watching Netflix or something. I don't know. And I can just tab out and answer your question real quick. Or maybe I'll be riding my bike and I won't be able to see it for a while, you know? So you never know. But don't hesitate to reach out if you do have questions. All right. We can't really have traditional office hours. So I'm just trying to be available and able to communicate with you guys. Okay, so that was that. Oh, you guys want to see what we did in trigonometry today? This is solving trigonometric equations. That was pretty fun. Using a cofunction identity right here, factoring out negative good stuff. All right, never mind. Delaney has canned that idea. Here, this one's for you, Delaney. All right, we good? Oh, October is going to eat that. Just kidding. Hold on. All right. Yeah, I got you covered. All right, so let's do today's material. So we barely started this yesterday, 3.5. All right. Oh, no. Gabe is here. Excellent. We can officially start now. Hope you're doing well, Gabe. We talked about the first two function transformations, that if we just add a number or subtract a number to our toolkit function, right? F is going to be our toolkit function. Then it moves it up or down. And we saw that over here. If blue is the square root function and we just add 2 to the end, that gives us this orange-ish thing, orangish brownish thing, which just get booped up. All right, and we saw this with all sorts of functions, right? We have a parabola, and we look at that parabola, and we, I don't know, subtract 5. It moves the blue graph down 5 units. All right, and you could do this with a whole bunch of stuff. We could do the, we do the nth root, or the cubed root of x, right, is a pink graph. Cubed root of x plus 2 is the green graph. It just shifts everything up 2. So that's how we started. We're going to do some examples on this, and then we're going to introduce more shifts, more transformations. We've talked about 2 transformations. There's 8 more. Wow. But really, there's only 5, right? Up C and down C. This is really kind of 1, but we're going to call it 2. Anyway, let's do some examples. All right, so example 1. Below is the graph of f of x. Plot f of x plus 2 on the same graph. Okay, and again, we know function transformations now. We know what's going to happen to the function. F of x plus 2 means we take all of the points in f of x and just shift them up 2. Zoop. That's the sound effect. All right, so let's get this graph of f, and then we're going to plot over it. Oh my word, my cat has woken up and he is very, very needy. Calm down, I'm trying to teach some college algebra. All right, so the function that they give you starts at 0, 0. It goes up to 3, 3. And then it stays there at 5, 3. And then it goes quickly back to 0. All right, so this is f of x. And now we are supposed to plot f of x plus 2 on the same graph. God, I got both of them today. October is really enjoying my chair, and my other cat is trying to scream for me from farther away. All right, you two behave. All right, so I'm going to use a different color. I would highly recommend you, if you don't have multiple colors of pens or pencils or something, I would highly recommend doing so. It's not a requirement, but it's going to be helpful. They like each other mostly. Sometimes they play aggressively. All right, this is really not going to work. So let's shift everything up 2 units, right? What does this mean? This means up 2 units. So this point jumps up 2. This point jumps up 2. This point jumps up 2. This point also jumps up 2. We just move all the points up 2 units. Okay? And then it's still going to have the same exact shape as before. So this is our answer. This is f of x plus 2. And that's really most of this part of the sum of the, it's a portion of the section. All right. And again, this book in particular really likes to ask questions in different ways. All right. So we're going to look at this. This is a graphical problem. We'll look at a problem with a table next. And then, yeah, mostly we're doing graphing and tables today. All right. How much harder does this get? Fair bit. Fair bit harder. But don't you worry about that. One thing at a time. One thing at a time. Example 2. Fill in the blanks. All right, so first row is going to be x. Second row is going to be f of x. Third row is going to be f of x minus 3. X is going to be 2, 4, 6, 8. F of x is going to be 1, 3, 7, 11. So all we do here is just move all the y values down 3 units. So the y value here is 1. We need to move that down 3 units. So it just moves to a negative 2. Okay, we're just doing the same thing here, but with a table instead of a graph. This moves down 3 units. The y value is what's getting subtracted. Goes to here. 7 goes to 4. 11 goes to 8. And that's all there is to it. For now. And that's vertical shifts. Horizontal shifts are usually a little bit more confusing. And that's what we're doing next. All right, so next up, we're going to fill in rows 3 and 4. Horizontal shifts. Right C, or let's say A. Right A and left A. We're going to show what that's going to be. So, let's look at this. Explain the table again, Bella. So when we have a plus or a minus, when we have addition or subtraction on the outside of a function, that's a vertical shift. All right. If we add or subtract something at the end or at the outside, it's a vertical shift. So over here, f of x minus 3 says we take the function f of x and shift it down 3 units. So if the f of x is 1 right here, then to shift it down 3 units, it needs to move to negative 2. If it's 3, down 3 units goes to 0. If it's 7, down 3 units goes to 4. All right. And now we're going to talk about horizontal shifts. So let's explore together. All right, let's explore together. We're going to start with our good friend y equals x squared. Everyone loves a good old parabola. So if we add something on the outside, right, then the green goes up. If we add something on the inside of the function, that's a horizontal shift. And you might be surprised to find out that it moved left. When we added 1, it moved to the left one, not the right. You might have expected it to go right, okay? But it doesn't. In general, and it's going to be a theme of this section, anything we do to the inside of the function kind of goes opposite of what you might think. Yeah, it's kind of backwards, all right? Inside is going to be horizontal stuff always. And it's kind of going to be backwards always. And then outside of the function will be vertical stuff. And we'll talk about it. And by the time we got this section, you'll feel maybe not good about it, but you'll feel something about it, right? So likewise, right, if we change the addition to a subtraction, it's going to move to the right. Okay? So, and that's what it looks like, essentially. And so this works for other functions too. Like, let's look at the square root of a function, square root x, right? If we added 1 or added 2 on the inside, it should move it to the left. And you can see, yes, when we added 2 to the inside of the function, the green graph started where it was, where the pink one was, but it got moved to the left over here. All right. Remember, on your exam tomorrow, you're going to have to talk about domain and range. And that can be helpful too when you think about domain and range, right? If I asked you, what is the domain of this green graph, or this green function, but you didn't get the graph, remember the inside has to be greater than or equal to 0. Or you could say, let's use function transformations. I don't need to set up an equality. What's the function transformation here? It's 2 to the left. So it's going to be negative 2 to infinity is our domain. And again, the domain is indeed negative 2 to infinity because that's the smallest the x value goes is negative 2. And the biggest it goes is off to infinity. Yeah, and honestly, you know, not going to pull any punches. This is one of the harder sections of the first half of the class. Actually, I would say this is one of the hardest sections in the first 2/3 of the class until we get to logarithms. I think logarithms are also challenging, but until we get to logarithms, this is going to be one of the most challenging sections. Okay? So on the one hand, that's hard, right? You don't want to hear that this section's hard. But on the other hand, it means that most of the other material is not as bad as this. Okay, so I don't know if that makes you feel better or not. But that's what we're doing here. So let's write that down. Let's fill in our table of transformations. So if we add something on the inside, it goes to the left. If we subtract something on the inside, it goes to the right. So the way that we write that is like f of x minus a is going to move it to the right a units. If we have f of x plus a, that's going to move it to the left a units. Again, it's going to be a big theme of this section. Inside stuff is horizontal. Outside stuff is vertical. So a vertical shift was adding on the outside, horizontal shift adding on the inside. And then inside stuff also kind of works backwards from what you might expect. So some examples, if we have y equals the square root of x minus 2, that goes 2 to the right. Or y equals the square root of x plus 2, that's 2 to the left. Boom, boom. So let's do some problems. Let's see this in action. We are on example 3. It may seem a little familiar. There's no deja vu going over here. Well, see if you get that tingly feeling in the back of your head. Below is f of x. Graph f of x plus 2 on the same axis, axes. All right. So it's going to start at 0, 0. It's going to go to 3, 3. It's going to stay there till 5, 3. And it's going to go down. This is the exact same graph as we did in example 1. But what function transformation are we doing this time? So if you forget your function transformations, we only have a couple now, but there's going to be a lot eventually. Just walk us through it, right? Something is happening on the inside of the function, so that means horizontal. Horizontal, inside. And since we're adding it, that's going to be a horizontal shift. Since it's on the inside, it's going to go the opposite way that you might expect. It's going left 2 units. So this is really important to identify before you do any problem. Indeed, if you identify it but still mess up your graph, you get a lot of partial credits just by identifying it. All right. So now we just take all of these points and we just shift this whole graph 2 units to the left. So 2 units to the left is right there. Boop, boop. This one goes 2 over. Boop, boop. 2 over. Boop, boop. 2 over. Boop, boop. Sound effects are important. All right. And then again, it's still going to have the same shape. It's just shifted a little bit. So the red graph is our answer. Yeah, there's a lot of weird plurals in English. Like we always say parentheses, but that's the plural. How often do you say parenthesis? I feel like it's pretty rare. Because usually we don't deal with a single parenthesis, right? Anyway, any questions on this? Otherwise, we're going to go on to example 4, which also might look a little familiar. Okay. Example 4. Below is f of x. Make a table for f of x minus 3. Yes, I'm definitely very smart. So here's the table. I'm going to give you, that's supposed to be an x. I can't salvage that. Table of x and f of x, where x is 2, 4, 6, 8. F of x is 1, 3, 7, 11. And I know, I got to stop you right here. I know you're going to say, hey, this is the same as example 2. Yes, it is. We're using the same examples to incorporate the new transformations, all right? You don't have to worry about too many new things at once. So over here, we're going to make a similar table, and this is where things get a little weird, so be a little careful. F of x minus 3. In example 2, what did we do? We said we were moving in example 2, we said we were moving down 3 units. So we changed all the y values and we lowered them by 3 to get -2, 0, 4, and 8. But here, what function transformation is this? Something's happening on the inside, so it's going to be horizontal, which means it's going to be the opposite of what we might think. This is moving everything to the right. 3 units. Yeah, good, Bella. Right 3 units. So if we're moving things to the right, we're not changing the y value at all. right? Just like example 3, we didn't change any of the y values of these red dots, only the x values. So similarly, we're only changing the x values here. So if we have a point 2 comma 1, right, because that's a point 2 comma 1, it gets moved right 3 units. It now becomes the point 5 comma 1. Right? But these horizontal ones usually look kind of weird to do. But again, if you just have the point 2 comma 1 and you need to move it right 3 units, it does become 5 comma 1. The y values are not changing here. So you just do that with all of the points. We're moving all of the points right 3 units, so the x coordinate is getting 3 units bigger. So this is going to be 7, 3 on this one. 4 becomes 7. Y value doesn't change. Over here, we get 9 comma 7. The x value grows by 3. We go 3 to the right. Y value doesn't change. This becomes 11, 11. And that's our answer right here. Questions on this one? After this example problem, I think we start getting into the more of the meat and potatoes of this section. All right, so hopefully you have the stomach for it. All right, let's do example 5. So below, Kinley does not have the stomach for it. Oh no. Well, oh my word, my cat is screaming his brains out. He really wants attention. Below is g of x, a transformed, we're going to go the other way this time, a transformed version of f of x equals x squared. This is one of our toolkit functions. A parabola. Relate g to f and find an equation for g of x. All right. So this is part of the problem. I'm giving this to you. F of x, or g of x starts at 2, 0. Also has the point 3 comma 1 and 1 comma 1. Again, it's a parabola. And then 0 comma 4 and 4 comma 4. So this right here is g of x. So the question is, what did we do to f of x to get to g? If we had a normal parabola, that's f. This is not a normal parabola. This is a transformed parabola. And what happened to this parabola we got right here? We moved it over. Yeah, very good. We moved it over 2 units. Right? It got G got moved right 2 units. So how do we do that? How do we move a function right 2 units? Well, horizontal shift right A means subtract A from the inside. So if it's right 2, we need to subtract 2 from the inside of the function. So all g of x is our original function, x squared, and we have to subtract 2 on the inside. That's our answer. And we can check our answer with Desmos. All right. Let's check our answer. is y equal to x minus 2. Aha, it is, yeah. That's exactly what we had, right? 2 comma 0, 1 comma 1, 0 comma 4. These are all these points that we talked about it. If we said it was x squared minus 2, then this would be subtraction on the outside of the function, at the end of the function. And this right here is down 2 units. All right. But here, how it's on the inside of the squaring, that means it's going horizontally. But here it's on the outside of the squaring, so it's going vertically. Good question. Thank you. And yeah, another way to have phrased this, if you wanted to, you could have also said that g of x is f of x minus 2, like this, if you wanted as well. And then, this is like a function composition, isn't it? Function compositions, hey! Remember this? That means we just plug in x minus 2 into f, which is the squared function. So it becomes x minus 2 squared, like this. It all ties together. What a coincidence, right? What a coincidence that we're doing this right after function composition. Because all of this is just function composition. All right. All right, so that's horizontal shifts. That's vertical shifts. What if we put them together? All right. There's no reason we can't shift it horizontally and vertically at the same time. Right? This is a parabola that got shifted right 2 units and up 3. And this is the start of where this section gets a little special, because there are going to be 5 function transformations that we talk about. Vertical shifts, horizontal shifts, reflections, vertical stretching, horizontal stretching. And by the time we get to the end of this class, maybe not today's class, but by the time we finish this section, we're going to be doing all of them at the same time. All right? This is where the fun begins. All right? So you can combine different things all at once. All right? As a side note, I love stretching. I stretch all the time. Like if I walk for more than like 5 minutes, I like to stretch afterwards. I stretch for an extremely long period of time just because I don't like sore muscles. And stretching it out after like you do a workout is a really good way to not get sore muscles. So, you know, just there we go. All right, so let's combine it. Baby steps, baby steps. But not like a human baby. These are like giant baby steps. If a giant had a baby, this is the kind of baby steps it'd be taking. So let's combine both things that we've learned about before we go on to the third type of function transformation. All right. And yeah, when we eventually combine everything together, you just do it step by step. So it's not like the problem gets 10 times harder. It's just more like you're doing 10 problems at once. I'm not really selling it, I think. We'll get there when we get there. All right. Let's combine everything together that we've learned so far. We have example 6. Yeah, forget I said anything, Delaney. Don't worry about it. Graph. Part A. F of x equals the absolute value of x. Oh, Jason, I thought you said this was going to get worse. There's no function transformations here. We just have to remember this toolkit function, the absolute value. All right. Yeah, 10 problems one after the other. 10 problems in a row. It's like going to one of those super fancy dinners where they have 10 courses. They're all really small courses, so you don't get too full. Same with these math problems. So hopefully you remember what the absolute value function looks like. Absolute value function looks like a v. Because all it does is if your input is positive, absolute value doesn't change anything. But if your input's negative, it turns it positive. All right, so remember, absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. Absolute value of 3, you get the idea, right? Yeah, it's a v, Stella. Good. Absolute value of -1 is positive 1. Absolute value of -2 is positive 2. And again, you see the trend. So this is the absolute value function, and it's one of your toolkit functions. If you memorize those toolkit functions that we've been talking about the whole semester, it will get much easier for you. So that wasn't too bad, right? But now we're going to do part B, of course, right? Part B says graph h of x, which is f of x plus 1 minus 3 on the same axes. So every time you're doing function transformations, you need to identify and write down what the transformations are before you even try to attempt the problem. Okay? So we need to figure out what's going on here. So we have a horizontal's inside, and vertical's on the outside. Remember that on the inside, it's kind of backwards from what you might think. So this part means we need to go to the left 1 unit. On the outside, that means we're going down 3 units. But that's all it is. You just consult, there's no table here. You just consult the table. There's no table there either. You just consult the table and see, what do we have? We have a plus 1 on the inside. What does plus 1 mean? Plus 1 means left 1. Just use your table. We have a minus 3 on the outside. What does a minus on the outside mean? Down 3. Okay, so that's why it's really important for you to be having this table in one location, and which is why I'm writing all the transformations in the same table, and so we're always going back to this table instead of just writing them down wherever we are in the notes. So watch this. You are going to laugh when you see how easy this is. All right, are you ready to laugh? Are you ready to guffaw? All right, because that's all we do. We just take every single point and move it left 1 and down 3. So this point goes left 1 and down 3. Right? Left 1, down 3. This point goes left 1 and down 3. This point, left 1, down 3. This point, left 1, down 3. The whole V goes left 1 and then down 3. Left 1, down 3. Left 1, down 3. And again, once you start filling it in, you really do see the pattern. It's still a V. Doesn't that make you want to laugh at how much that wasn't as bad as you might have thought? Ha ha ha. All right. I laughed. Although I confess it was not a genuine laugh. I kind of forced it. You should play that Mary Poppins song. Hold the cat. October's sleeping and my other cat doesn't like being held. Not going to wake her up. So that's what you're doing here. Identify the function transformations. These are very important. And then just do that to every single one of the points on your graph. And it should look pretty similar. I already have the wig planned on Monday. You better remember. And then you really will laugh. All right. Have some patience. Let's do another problem, unless there are questions here. You have a note? Good to hear. I have a brown wig, a black wig, multiple blue wigs, I think multiple red wigs. I have a blonde wig. I think I have 2 blonde wigs. We got a lot. All right, a lot of options. Haven't decided what I'm going to break out for you guys, but it's going to be good. Let's do example 7. Write a formula. Become area. I don't really know if it's very professional, if the college would really approve me teaching math with only a seashell bra and a long female wig. I might get a talking to. Write a formula for the below function. Yeah, as to the reason why I have the wigs, you will just have to wonder. I might tell you one day. All right. So now I'm going to give you a graph, and you're going to give me the formula for it. All right. Let's say we start at 1, 2. And then we go to 2, 3. And then 5, 4. We keep on going like this. The function looks like this. So there's a couple steps here. First, we have to identify what the toolkit function is. And then we have to identify the transformations. And then we have to find the function. So as easy as 1, 2, C. So, what toolkit function is this? What function has that shape that we've talked about? Some of you are probably having internet connections, so your connection issues, so you're probably unable to get your chat messages across, but I know that you're typing in the square root of x. This is a square root function. And then what's happening to the square root function? Normally the square root function starts over here. So what's happening to the square root function is got moved over 1, right 1, and up 2. So we just have to figure out how to write this with a formula. We need to go right 1 unit and up 2. So we consult our little table and say, let's see here. We need to go right 1. So that's going to be subtracting 1 on the inside. And up 2, that's going to be adding 2 on the outside. So subtract 1 on the inside, add 2 on the outside. Or you get something like this. Subtract 1 on the inside, add 2 on the outside. And then again, f is just a square root function, so we're going to replace the f with the square root function. So, final answer is going to be g of x is the square root of x minus 1 plus 2. Example 7 is one of the most important examples of this entire section. And I can almost guarantee that your quiz on Tuesday, that's when you're going to be quizzed about this, is going to have a problem that looks like this. Okay? These are good problems. So you need to know what your toolkit functions look like. You're not just going to magically know them. You got to study. Got to do some problems. And you need to be able to use your function transformations. Okay? Right 1, up 2. This is the right 1. This is the up 2. All right. So that's that. Are you ready for our third function transformation? Ready or not, here we come. So let's say we have a parabola. I love parabolas. What happens to this parabola if I just put a negative in front of it? Well, if I put a negative in front of it, it makes all the y values negative. So if we have a parabola with everything positive and I make it negative, it's just going to flip upside down. That is a reflection. Boom. Look at this. It's like it's dancing. Kind of cute. All right. So if we add a negative on the inside, we add a negative on the outside. Remember, outside means vertical stuff. So it's vertically getting reflected around the x-axis. Good. And so if we can reflect it on the x-axis by doing it on the outside, a vertical reflection, doesn't it also make sense that we might have a horizontal reflection if we do something on the inside? Outside is vertical, inside's horizontal. All right? So for example, let's look at some other function. All right, if we're looking at the square root function, and again, just like before, if we put a negative on the outside, should reflect it upside down. Okay, good. The green just get reflected upside down. All right. If we added the negative on the inside, remember inside is horizontal stuff, it should get flipped the other way, left to right, about the y-axis. Wow. What do you know? I was right. What a coincidence. All right. Inside is horizontal stuff. Outside is vertical stuff. Right? Just like if we add something on the inside, that's a horizontal shift. We add something on the outside, that's a vertical shift. So we could do this with like a whole bunch of functions, right? What's another good toolkit function? How about 1 over x? We haven't talked too much about 1 over x. Oh, absolute value. That's a good one, actually. Right? If we put a negative on the outside, it should flip it upside down. We get the green as the flipped upside down. Something kind of funny happens, right? What if we put the negative on the inside here? Nothing changes, right? Because if we flip this left to right, flip it about this y-axis, well, then it's still the same thing because it's already symmetric. Right? If something's symmetric, what's called an even function. I don't think we've talked about even functions yet. Oh, we're doing that half a page down. Then it won't change. All right, so let's summarize that in our table. Let's add a new column to our table. All right. Vertical reflection. And horizontal reflections. This is sort of, I'm going to confess something to all of you. This is sort of an imprecise definition. The really precise thing to say for a vertical reflection is reflecting about the x-axis. Horizontal would be reflecting about the y-axis. Well, I find that these terms can be very, very helpful. But I should have also left a room to write a note about what the precise terms for this stuff is. All right. So vertical reflection is, again, about the x-axis. And horizontal is about the y-axis. There's no room for that second one. But that's the idea. And again, if it's a vertical, it's going to be on the outside of the function, negative f of x. If it's horizontal, it's going to be on the inside of the function, f of negative x. All right. And these two are the last nice transformations. The last two pairs of transformations are, let's call them unpopular. All right. So an example of this, right? If we had y equals negative x squared, that would flip it upside down. If we had y equals the square root of negative x, that flips it right to left. All right, this is a good time for to take attendance. I did forget to take attendance yesterday, so I just gave you all the benefit of the doubt and assumed everyone was here yesterday. Seemed like the fairest way to do it, or at least the way that was the least punitive. But today we will be taking attendance. So send me a message in Discord for your attendance today of the name of a fruit, such as a melon, a lemon, strawberry, tomato, grapes, etc. So, oh man, I have so much mud on me. I didn't even realize it. I went biking this morning. A couple of little things there. All right. So go ahead and message me for your attendance today, and then we're going to keep on going, because we have now covered reflections. We're on example 8. There's a lot of examples in this section. It's a long section. All right, which is why I will be okay even if we don't finish today. So example 8, what do you got? Reflect s of t, which is the square root of t, and write the new function. Write the equation of the new function. So in part A, do it vertically. Again, that means about the x-axis. So we're just going to consult our table. This table is going to be very useful for you. Do not misplace it. So we need a vertical reflection about the x-axis. So vertical reflection says, okay, that means we need a negative on the outside of the function. A negative in front of the whole function is going to make it vertical flip. So a negative out in front just means in front of the square root. Okay, let's call this f of t. Just put a negative in front. And that's it. That's all there is to it. That's 8a. So for 8b, what about horizontally? Again, that means about the y-axis. Just consult the table and say, well, table, how do we reflect this? Horizontal reflection, let's see, table says you put a negative on the inside of the function. Okay. So yeah, it's just going to be something like g of t equals the square root of negative t, negative on the inside of the function. That's all this is. Any questions on this? Okay. And I think what we're going to do today is, let's do 2 more examples, example 9 and 10, but then stop right before we start talking about even and odd functions. We'll finish up the section on Monday, and then we'll end a little early, and then I will answer questions related to the homework or the exam for the last like 30 minutes of class, or not 30 minutes, for the last like 15 minutes of class or something. All right. So let's do 2 more examples, 9 and 10. So consider a function that you may or may not have seen before. where x is 2, 4, 6, and 8. And f of x is 1, 3, 7, and 11. The same old function. It's back. Brock, don't you miss college algebra? You didn't even get me for college algebra. We need to fill this hole in your life, Brock. You had me for the class before and the class after. You're missing out. Function transformations too, Brock. Not it, Chief. Oh, man. All right. Let's ask the question. Make a table for g of x is negative f of x. So what does this do? First off, let's identify what transformation this is. What transformation is this? Negative on the outside of the function. Consult the magical table. Negative on the outside of the function means a vertical reflection about the x-axis. Yeah, flipped upside down. All right, so this is vertical reflection. So what does that do? It changes all the y values, right? It reflects all the y values. So when we make our table, we're just reflecting all of the y values. The x values are not being changed when we flip something upside down. X value doesn't change. It's only the y values that change. Specifically, you get flipped upside down. So if you're at positive 1, flip that upside down, you get negative 1. Positive 3, flip that upside down, you get negative 3. Positive 7, upside down is negative 7. Negative 11, right? That's it. Part B, what about for h of x is f of negative x? What transformation is this? Well, this is just a horizontal flip-in, right? This is a horizontal reflection. And remember when we flip something horizontally, the y value doesn't change. Only the x values get flipped. Okay? Yeah, so all of these x values are just becoming their negatives. So the y values are not changing from the original. Y values are still 1, 3, 7, and 11. It's just the x values that just get reflected. Negative 2, negative 4, negative 6, and negative 8. Yeah, if you flip the x, if you exchange the x's with the y's, that's actually the inverse function. And we'll talk about inverse functions on Tuesday. That'll be 3.7. It's the very next section right after that. All right, let's keep going. We're on fire today. Example 10, and then we're going to do some review. I think October just coughed. So, you guys ready for an application problem? Because ready or not, here we go. So, a common model, I don't know how common it is. I make no claims to how common this is. But a common model for learning it definitely has an N right there, is the function k of t is equal to negative 2 to the negative t plus 1. My notes are a little bit messy right here. I think that's what it is. All right, so the question is, or let's explain what this is, right? Where k is percent mastery after t sessions. All right. So this is a transformation of y equals 2 to the t. That's an exponential function. We haven't talked about exponential functions, but I'll give it to you for this function, for this example. Graph k on the same axes. So I will give you the function 2 to the t, and then you have to give me this learning curve. So 2 to the t looks like this. When t is equal to 0, we're at 1, and then 1/2, then 1/4, then 1/8. When it's 1, it goes to 2, 2, it goes to 4, 3, it goes to 8. This is an exponential function. You may have seen a lot of information about exponential functions recently. People like talking about exponential functions right now. Exponential functions are hot right now. We'll talk about those. Wait. You're just going to have to wait. We'll talk about those later in the class. All right? So, let's do some transformations. What transformations do we have? Oh, we got a lot of transformations. We got 2 negatives. We got a +1. We got loads to do. All right. So, this negative on, let's start with the negatives. Negative on the outside is a vertical reflection. Negative on the inside is a horizontal reflection. We got a double reflection. Wow. And then a +1 on the outside is a vertical shift up 1. So we have to do this to all of these points. And this is where you have to be pretty careful. All right? It's a little tedious, but it's not too bad. Just be careful. So, let's start with this point. This is the point 1/4. A vertical reflection flips it upside down. We're at -1/4. And then there's a horizontal reflection, which changes the x-coordinate from -2 to +2. Now we're at 2, -1/4. Then we move it up 1 unit. So it becomes 3/4. Over here. Yeah, it can be a good idea to make a chart for this as well. To reflect 1/2 over, it becomes -1/2. Reflected across this axis, it becomes +1. Move it up 1. We get that point. Reflect it vertically, upside down. Reflect it horizontally, doesn't move, up 1. Reflect this vertically, goes down to -2. Horizontally, goes over to -1, up 1. Goes like this. This point, reflect vertically, becomes -4. Reflect horizontally, -2, up 1 to -3. And we get something with the same shape, like so. Kind of looks like a logarithmic function. We'll do more of these, so if example 10 was rough, don't worry. We have a lot more stuff similar to this. And yes, the order does matter. We're going to talk a lot about what order to do things in later on in this section as well. This is kind of like a example where it's like, hey, this is what we're going to be doing at the end of the section. Hope you're ready. Hope you're excited for it. I think everyone's probably checked out at this point. It's been a long lecture on function transformations. So we're going to end a little bit early. I don't know how early we are. Yeah, like 12 minutes early. If you have any questions about the exam, though, now is a good time to ask them. If you want me to look and talk about anything from the review, if you want to ask any questions about what's going to be on the exam, how the exam is going to work, now is the time to do it, all right? Or if you want me to go over any topics that are going to be on the exam as well. Yeah, I can do a homework question. Absolutely. Give me the section and the number. We can talk about that. 3.2. Okay. Do you have a specific problem in mind or just like a certain type? Two. 7. So finding the domain and range for all of these. So for these ones, sorry, just domain. Domain is just everything that you can plug into the function. So, excuse me, a lot of times it's easier to ask what you cannot plug into the function. Number 7 is a quadratic, right? This is a quadratic equation, a quadratic function rather. I mean, you can plug in anything you want to a quadratic function. There is nothing that's going to cause you a problem here. So your domain is all real numbers. So something like 7 is really nice, as opposed to number 9, which has a square root. And if you have a square root of a negative number, then you get complex answers. And we don't want these in a real valued function. So for something like 9, you have to look at the radicand, the 6 minus 2x, the inside, and set that greater than or equal to 0, because we don't want it negative. And if you get something like 14, if you get a fraction, it's kind of small. If you get something like 14 and you get a fraction, you have to make sure that you're not dividing by 0. And that's how you would approach something like 14. Okay. Other questions or follow-up questions? Yeah, 13 is a cubed root function. Well, remember what cubed root, oh wait, I got rid of Desmos. Remember what cubed root functions look like, right? Cubed root functions are one of your toolkit functions. So it's certainly a really good function to be familiar with. Cubed root functions look like these. The domain of this is all of the x values. And notice that this goes off forever. This has every x value you can possibly want. And that should make sense, given what we know about cubed roots. Because remember that one of the big things that we talked about in 930 was radicals. And if there was an even index, like a square root, then if the inside was negative, it was not real. But if the index was odd, like a cubed root, the inside being negative wasn't a problem. So 13, we can actually take the cubed root of any number and get a real number. All right? So it's going to be all real numbers is going to be your domain for 13. Good. Any other questions? All right. Well, thanks for asking, Bella. Anyway, if you have further questions, you can always catch me on the Discord. You can either send it to me individually, or you can just post it under the 1400 questions channel. And that way, other people can get your answers as well. All right. Yeah. Have a good day. Good luck on your exam tomorrow. Should be fun.